Welcome to Module 3, everybody. This week we're going to talk about MIPS machine and assembly language. I'm sorry for the difficulties that I had on Monday night with the office hour, Tuesday night. I just had some issues with the Wi-Fi and couldn't seem to quite connect, and so I kept dropping. But I did want to get in touch with you guys and hopefully go through some demos. I've taken them from the reading. I'm sure you guys have done the reading at this point, but hopefully I can go into it a little bit more depth and detail and clear up any questions or maybe misconceptions you may have had. And certainly if you have any questions as a follow-on to any of this, please always feel free to email me. We can set up a time to get online and do a Google Hangout, or we can talk over the phone to kind of discuss some of these concepts more. But please feel free to reach out if you have any questions at all. So kind of following the reading a little bit, the first thing we'll talk about this week is what an instruction set architecture is. And you'll see this word come up quite a bit. And instruction set architecture, we obviously abbreviate ISA. And in the course of this class, right, the one that we're talking about is MIPS, which we've talked a little bit about at this point. Some other common instruction set architectures are ARM. Probably heard of that. Intel's IA32. And so on. There's a bunch of these. Okay, so all an instruction set architecture really is, think of it as the vocabulary or the language of the hardware in a computer. It's the vocab of the hardware. So we saw in the first office hour how we formulate an instruction, and I went in a little bit about how an assembler will take the intermediate assembly code and then turn that into the binary code that an assembler speaks. So the instruction formats that are supported, we talked about the register type instruction, which was an R type. And one of the examples that we saw of that was addition. So we could do something like this. Add and put the result in T0 of the addition of, say, register S1 and register S2. Okay, so this is an R-type instruction. So this is an example of an instruction from the MIPS architecture. Okay, so MIPS computers understand this instruction format. They understand how to speak it and how to do the computation. So whenever we talk about an instruction set architecture, we just simply mean the vocab that the hardware is willing to speak. Okay, so the next thing that's important to understand, we've probably heard this word a lot at this point, and we're going to talk about registers. And so we've seen this word come up a bunch, but what a register is, it's a data storage location that's pretty close to the CPU. Most of the time it's right nearby. And the reason that this is the case is because you want certain data accesses to happen very quickly. And an example of a slow data access is if we had to reach all the way out to the computer disk, the hard drive, and pull data in off of that. That would be slow. Something that's a little bit faster than that is to store something in RAM and have to go in and fetch it and pull it in and out each time you need to. Okay, but the quickest way to do these memory accesses are to use registers. And in MIPS, the registers, okay, a MIPS register is 32 bits of storage. Okay, so 32 bits divided by 8, that's 4 bytes. And we have a special word for a 4-byte entity that comes up so often in computer architecture that a 4-byte entity is known as a word. So 4 bytes together, or 32 bits, is known as a word. So something you're going to want to keep in mind. Okay? So again, registers provide us very fast access, which is really nice. And we started to see some of the registers that are in use in MIPS in the first office hour. Remember things like, in the textbook they use the T registers. The T0, for example, is an example that is a register that might hold a temporary value. And on a couple occasions, you'll be asked to translate from a C or a Java program. You'll be asked to figure out how it would be compiled and assembled. So when you're working with the variables inside of a programming language, the textbook represents these using variables like S1, S2, and so on. So these are your C and your Java, your higher level programming language variables. Okay, so if you see those, that's what that's about. So I'm going to go ahead and try to clear the screen here. Perfect. Okay, we're going to take a look at an example real quick. So an example you'll find in your textbook looks like the following. This could be C code, it could be Java code, but we have this. It says F is equal to G plus H minus the sum of I and J. Okay, so the question is, once the compiler takes this and translates it into assembly code, what is the MIPS assembly code going to look like? Okay, so we have to think back to our order of operations here. Notice that we're doing the G plus H and the I plus J inside of parentheses. So we're going to have to do those first. Okay, and you can see that it's addition, which is one instruction that we talked a bit about so far. Okay, so I think a natural place to start is to let you know which registers here correspond to which of these variables. So F, 0, 1, 2, 3, and 4. Okay, so F is going to be register S0, G is going to be S1, H is S2, I is S3, and J is S4. Okay, so these are the registers that are going to logically correspond to these variables in the source code. Okay, so obviously you see that we want to do S1 plus S2. We also want to do S3 plus S4. Okay, and then we're going to subtract the difference. So let's start with this part right here with S1 plus S2. Okay, we have this add command. Like I said, we've looked at this a little bit, so we can do something like this: add and store the result into T0, which is just a temporary location. Okay, register S1 and register S2. Okay, so what this is going to do is going to add the contents of S1 and S2, which we know from here are G and H, and it's going to store them here in this temporary location T0. So that's going to hold the first sum for us right there. Okay. And in a similar way, we're going to do the same thing for I and J. We're going to do another add instruction. And this time we're going to store the result in T1 because T0 is already holding the result of the first computation. So we're going to take T1, and that's going to be the sum of I and J, which is register S3 plus register S4. Okay, so now we've completed the addition portion. The only thing we have left to do is subtract, and keep in mind we want the result to end up here in register S0. Okay, so we actually do have a subtraction instruction here, and it's also an R type, so it acts exactly like the add instruction does. So we're going to do a sub for subtract. We want our value to end up in S0. And of course our two sums are stored right here in T0 and T1. And so we want T0 minus T1. Okay, so this right here is the result of the compiled version of this source code. So this is your C or your Java right here. Once it goes through the C compiler and it gets output in MIPS assembly format, the code is going to look exactly like this. Now that we've taken a look at how an arithmetic instruction works, we're going to look at another class of operands in the MIPS instruction set. And we're going to look at something which are called memory operands. Okay, so slightly different than the ones we just looked at. So we're going to look at, and please forgive the handwriting. I'm getting used to writing on a tablet computer, the kind that fold over backwards, and I can finally write on them. So I'm trying to make it as neat as possible, but it is a little tough up front here. So the idea here is this. I mentioned to you that MIPS has 32-bit registers, and usually most computers nowadays have 32 of those 32-bit registers, so 32 words worth of register storage, which really, as you know, is not a lot. Okay, so when we need to store things that are larger than a byte or larger than 4 bytes, let's say we have a 10,000 byte array. something like that, where we want to store a number of objects or some sort of fancy data structure. Those things have to be stored in memory. Okay, they can't be stored in register space because there's just not enough storage there to be able to do that. Okay, so something to keep in mind is that in order to facilitate this, if MIPS wants to do an operation on a piece of data from an array, then it's going to have to transfer the data back and forth from the array. Okay, and these types of instructions are called data transfer instructions. So something also worth noting here are our data transfer instructions. Okay, two of the primary ones that we're going to work with in this class, one of them is called SW. Okay, the SW instruction stands for store word. And what this means is we're going to take, when we do a store, we're going to take a value from a register and we're going to move it to memory. Okay, now contrast with the opposite. So we have an LW command in MIPS, and that means simply load word. And as you might have guessed, it's just the opposite of a store word instruction. So what load word does is it goes to memory, gets a 32-bit or a 4-byte or a 1 word, those are all synonymous, value, and then pulls that into a register so that we can then operate on it. Okay, and a very, very, very important, a critical thing to understand about MIPS as an architecture, and this is true of many of the ISAs that exist today, so I'm gonna put a big fancy star next to this one, and since I'm using a new pen and computer, I'm gonna start in red. Okay, and it's important to know that MIPS uses something called byte addressing. Okay, we're going to see what this means in a little bit, and it'll make more sense after I explain it, but it's something that's very, very, very important, I think. Okay, so just keep this in mind as we go along. We'll talk about it here shortly. But MIPS as an instruction set architecture uses byte addressing. Okay, so I think we might be a little better off if we kind of motivate this with an example. So let me clear the screen here. Okay. And there's an example in the textbook. They give you a piece of source code that looks something like this. And again, this could be Java, it could be C. Okay, they say a variable G is equal to H plus the 8th element of an array called A. Okay, and then they tell us a couple of other things. They tell us which registers correspond to which of these variables. So I think they assigned S1 for G, S2 for H, and then S3. Okay, this guy has a special purpose. S3 actually, we refer to this as a base register. The base register. Okay, and the reason we refer to this as the base register is because it holds the base address, which is the very, very first memory location where the array called capital A starts in memory. Okay, so the base register holds what we call the start address of the array A. Okay, so now we have some reference. We know where A starts. And we know that we want to go 8 bytes into that array because of the 8 right here. And then whatever element is there, we're going to try to pull that into the register, into S3. And we already have H stored in register S2, so then at that point, all we have to do is add them together. Okay? So again, keep in mind from the slide that I just cleared, MIPS uses byte addressing. Okay, so we're going to start with a simple example here where we focus just simply on single bytes. So when it says A of 8, that means go 8 single bytes into the array. Okay, so 8 bytes only. And I remember when I said on the previous slide that I had up, we have a load word instruction. And load means go into memory, pull something out of it, and store it in a register. Okay, so if you think of the array A, pictographically, you might want to look at it like this. I'm not the best artist, I'm sorry. So 1, 2, 3, 4, 5, 6, 7, I think I'm probably one off, 8. Okay, so this register S3, we said it stores the starting address, which is right here. This is the beginning of the array. Okay, so let's say that the memory address for that guy is something simple. It's 0x00. So that's the starting address. So this box I'm drawing around it, this corresponds to the register S3. Excuse me, sorry about that. Okay, so that corresponds to this guy right here. And now what we're saying is jump ahead 8 bytes. So 1, 2, 3, 4, 5, 6, 7, 8. So we're saying jump ahead right here and then give me whatever's at that memory location. So whatever's in here is what we're after. Okay? So all we simply have to do is use the load word instruction. The load word instruction works as follows. We see here that we want to read it we want to read it into a temporary location. So the place where we want to load the word into is going to be done right here. So we're going to load it into T0. And since S3 stores the base of the array, and we want to go 8 bytes beyond the start of S3, the way we write that in the load word instruction is just like this. It means 8 bytes away from, and then we tell it which register we want to go from, which register contains the starting address of that array. Of course, we know that that's S3. And that's it. This is the instruction right here. Okay, so this says go get the address out of S3. What address is that? Well, we know from over here on the left that that address is 0, 0. Then we're saying in our load word instruction, add 8 bytes to that. So jump ahead 8 bytes, which we saw here. 1, 2, 3, 4, 5, 6, 7, 8. 8. Take that value that we colored in here in black, and whatever value is there, whatever it may be, okay, take that and store it right here inside of T0. Okay, so I hope that's clear. I know it can be a little strange to hear it the first time. There's kind of a lot of words flying around, but if you have any questions, let me know. Okay, so now we have that inside of T0. And what we want to do, remember our goal here up in the equation is we want to add it to H, which is that value is stored in S2. So now we just want to add them together. We want to add T0 and S2, and we want to store that result in S1. And that's just our good old add instruction. Okay, so the way that works, remember we say add sorry about that, still new to this pen. It has a couple buttons I didn't mean to hit. So we want to do our add instruction here. We want to store the result in S1. And the two registers that we want to add together, remember, are right here, S2 and T0. So add S2 and T0. Okay. And that will accomplish this source code that we have right up here, our C or our Java code, whatever this may be. Okay, so just to recap here, with this load word instruction was step 1. Okay, the first thing we did was started the address contained inside of S3. As we see over in the box on the left, that address contained inside of S3 is 0x00. Then from there, we want to jump ahead 8 bytes. Okay, in this case, we're just talking single bytes. Pull that value out of the register, or out of memory, and store it in the register called T0. Once that's in T0, the second step here is just very simply to add what we just pulled in from the array to what we already have in S2. And as you see up above in the line of source code, that's the value for the variable H. So then we just simply add these two things together and store them in S1. which corresponds to our variable g, okay? And then these two lines here are the MIPS assembly code that correspond to this line of either C or Java. In the previous example, we saw the load word instruction, and the key thing to note, remember I mentioned that MIPS uses something called byte addressing. Okay, in that case, that was a simple example. We went 8 bytes into the array that was called A. We pulled out the value, we added it to another register, and then stored the result of the addition in a third register. Okay, in MIPS, there's this concept of something that's called alignment restriction. Okay, and remember that most entities that we deal with in MIPS, certainly the registers, are 32 bits or 4 bytes or 1 word long. So what we mean by that is every time you address a word in memory, okay, it must be on a 32-bit boundary. And so therefore, it's always going to be a multiple of 4. And just to demonstrate that a little bit, I'm just going to write a little memory array here, or not so little, and it's going to look like this. Each of these boxes are going to represent 1 byte. Okay, so this memory address starts at 0x00, which means that this is 0x01, 0x02, and 0x03. Okay, so that means we've taken up this box, 2, 3 bytes, 4 bytes. Okay, so here's our 1 word right here. So that means this next memory location here is 0x04, 5, 6, and 7. Okay, so this is another word right here. And then the next word starts here, 07 to 08, 9, and of course this goes off 10 and 11. That'll be our next word. So you can see here that the words always start on a 4-byte boundary. In other words, what we can't have happen, and this is a restriction on the MIPS end, okay, you can't have something like this where 0x00 is the first memory location. Okay, we can't start our word here at 0x01, 02, 03, 04. You see here how we skipped this first byte? We're not using this, and so that means our word is right here. Our word goes from 0x01 to 0x04. We call that unaligned. Okay, so we can't have that in MIPS, so always at the start of a word is going to be on a 4-byte boundary. So 0 is going to be your first word. 4 will be your next one. 8, 12, so on and so forth. Okay, so the difference here is that basically when we're going to go into an index into an array, like we did in the first example just a second ago, we went in a byte at a time, but really what we should be doing is going in a word at a time. So we're just going to simply multiply things to scale it up from a byte to a word. So namely, we're going to multiply the memory locations by 4. Okay, so if that doesn't make sense, we're going to see an example of it right now, but just please understand what I mean by this thing called alignment restriction. It means that words must start and end on a 4-byte boundary. Okay, so they have to start at 0. They will always start at multiples of 4 all the way throughout the memory space. Let me clear this, and let's go through an example also from the textbook, but I hope I can hit it in detail for you. So we have the following operation. We want to do this. We want to set the 12th element of A equal to whatever's in variable H plus the 8th element of A. Okay, this is what we're being asked to do. Now the key thing to remember here is look at this number 12, okay, and this number 8 right here. In the previous example that I just showed you, those things corresponded to single bytes, but that was just for simplicity's sake as a nice intro example to figure out how to access the different indexes in memory. In this case, please think of them as words. So the 8 really corresponds to 8 words, right? And remember that a word is 4 bytes long. So this 8 really corresponds to, sorry, let me get my pen back. This is really means 32 bytes. Okay? And this is how MIPS works in general. Again, the problem that we just saw was just kind of an intro to get you warmed up and thinking about how to access the elements in an array. And same thing here, this 12. Okay, it's 12 words, and one word has 4 bytes, so 12 times 4. So this means go 48 individual bytes into the array A, and that's where we're going to store the answer. Okay, so I hope that's clear. When you see these numbers now, we're not usually talking about individual bytes. The 8 stands for the number of words. Okay, so I hope that's pretty clear. So let's go ahead and step through this problem. So the right-hand side of this might look familiar to you. Okay, this was what we had before in the previous problem where we needed a load word because we wanted to go 8 words into the memory array called A. We wanted to pull that value from memory into a register. And remember, we used the load word instruction to do that. Okay, so let's start by addressing this part right here. Okay, we're going to use a temporary variable called, temporary register called T0. So we're going to do a load word into T0. Okay, now here's the slightly, very, very slightly complicated part. Remember that MIPS uses byte addressing. Okay, so MIPS does byte addressing. So please remember that this 8 right here is not in bytes. It's in words. Okay, so how many bytes are in a word? There's 4. So in order to go 8 words into the array, we really need to go 32 bytes. And since MIPS uses byte addressing, we tell the load word instruction, hey, load word, please jump 32 bytes into the array, and then pull out the value there, which, by the way, I forgot to mention, that's stored in S3. That's the base address. It's stored in S3, so let me write that up here. S3 has the base address. H is stored in S2. And then also over here, this is the same array A, so the base address is stored here in S3. Okay, so I just want to make clear one more time, the reason we use a 32 here, the 32 is byte addressing for this number 8 right here, which is in words. So basically all we're doing is taking that 8, we're saying, okay, 8 words, how many bytes is that? Because that's how far into the array I need to jump to get the value. Oh, there's 4 bytes in one word, so there's 32 bytes in 8 words. Therefore, I'm going to tell my load word instruction right here, hey, go ahead and jump 32 individual bytes into this array. And that's the same thing as jumping 8 words. So I hope that's clear. Whenever we use the load word instruction, you want to take the array index right here and you're going to multiply it by 4, and that's going to give you the number of bytes that you need. So I hope that's clear. If there's any questions about the difference between byte and word addressing, I hope you guys will please give me a shout so I can try to clear that up for you. Okay, but so now that we've accomplished that, sitting in T0, we have A of 8. We have the entry from memory that's an index 8 words. Okay, and what we want to do is we want to add that to H. So that's as simple as adding T0 and S2 right here. We want to add those two guys together. This S2 right here. So that's our simple add instruction. Okay, so we're going to store the result in T0. And what do we want to add together? We want to add together T0 and S2. Okay, and this is perfectly safe to do, by the way. I know that I reused T0 here, right? But that's actually perfectly safe. It will pull the value out and add it to S2 before overwriting T0 with the final value. So this is perfectly safe. You're not going to lose the value that was in T0 by doing this. Okay, so now we've completed the right-hand side. Okay, but now we see on the left-hand side, we want to take the result of that addition, which is now stored in register T0, and we want to move that back out to memory. And specifically, we want to move that out, get my pen back, we want to move that out 12 words into the array called A. And recall that that array starts at the address contained in register S3. Okay, so we have something in a register here, and we want to go out to memory. And remember that when we want to go from a register register to memory, that's our store word instruction. Okay, so it's the opposite of a load word. Okay, so that's exactly what we're going to do here. So we're going to use the store word, and the store word operates just like, or very similarly, I should say, to the load word instruction. The syntax is almost the same. So we're going to do a store word. Now we know that T0 is the register that's holding the value of the addition. So we want to store whatever's in register T0. Okay, where do we want to store it? Well, we want to store it 12 words into the array called A. But remember, we need to convert words, these 12 words here, to bytes, because MIPS only does byte addressing. Very simple, there's 4 bytes in one word, and there's 12 words, so we're going to do 4 times 12. That means we want to go 48 bytes into that array. And again, that array, the beginning of it, the base register, is stored in S3. Okay, and then this code right here is exactly what is going to be compiled for you from the high-level language, whether it's C or Java that's up at the top. So just to recap this, what we're saying here is number 1, go 32 bytes, which is the same thing as 8 words, from whatever S3 here is pointing to. That's the start of the array. Go 32 bytes in, take that value, move it from memory to register T0. Then we're saying add the contents of T0 to the contents of T2, and then temporarily store that result right here back in T0. And the final step here, the store word, step 3, this is just going the opposite. It's going from the register, so we're going from T0, and then it's asking, well, hey, where do you want me to store this in memory? And we're telling it, hey, I want you to store it 12 words, which is the same thing as 48 bytes, from the start of the array A. So count 48 bytes in and then store it right there. Okay, and that completes the example. So if you have any questions about how the load word or store word, those data transfer instructions work, please let me know. And some people get a little bit tripped up by converting these, the 12 here and the 8 from a word to a byte address. So if you have any questions on the byte addressing portion, please also let me know there too. The final type of instruction we're going to talk about today, I'll clear this out here, is called an immediate instruction. So it's an immediate. An immediate instruction is nice and simple. It's very straightforward. And what the immediate instruction does is it allows us to save from wasting an instruction to have to load something. So if we wanted to, say, add a constant value to a register, okay, so we wanted to add the number 1, let's say, just to increment like a counter or something like that. If we want to do that in a register, based on what we learn now, we would have to go into memory, do a fetch, which is a load word, load that value into the register, do the addition, and then we have to do a store word and move that output back to memory. Okay, so it would have to look something like this. We need a load word, and say we loaded, let's just say we knew where the number 1 was in memory. So we would load that into T0, and let's just say it was 4 words away from, it's making something up here, S0. Okay, so that loads from memory something into T0, and let's just pretend that's the value of a 1. Okay, then we're going to add that 1. Let's say we wanted to add it to T1. T1, T1, T0. So we're taking the 1 that's stored here in T0, we're adding it to T1, whatever is inside of it, just some variable we don't know at this moment, and we're storing that back inside of T1. So we've just added 1 to whatever was in T1, and now we have to do a store word. Okay, so now we take that new value that's sitting in T1, and then we would write it somewhere out to memory or something like that to be dealt with later. So it's kind of unfortunate that we don't have a way yet, which we will in just a second, we don't have a way to just simply add an integer value directly to the contents of a register. Okay, so that's what an immediate instruction is going to do, and I'm going to show you how to do that right now. Fortunately, it's nice and simple. This is a pretty quick tutorial on an immediate type instruction. But usually the immediate type instructions, they just add an I to the end of existing instructions. So we have an instruction that sometimes we call a quick add or an add immediate. Okay, and the way that works is just like this. So we're going to do the add immediate, which is add I. And we're going to store that result in, let's say, S3. And we're going to say S3 and the number 4. Notice we're not giving it a register here. Up until this point, we've always given it a register. So S2 or T4 or something like that. But now we're giving it a hard-coded integer value. So this is the actual integer value 4. So what we're saying is go into S3 right here, pull that value out, add 4 to it, store the result back in the register S3. Okay? So it's a very, very simple way to do it. And same thing, there's also a quick subtract. There's a sub I. So SUBI. If we wanted to subtract 1 from something quickly, let's say we had something stored in S4, and you just wanted to subtract 1 from it, comma 1. Okay? That's going to do S4 minus 1, and it's going to store it in register S4. So S4 is equal to S4 minus 1. Okay? So again, the big difference here is that these values, this 4 and this value number 1, these are actual real integers. We're not pulling from memory. We're not we're not pulling a value out of a register. We're just doing the add directly there. So that saves having to do those additional memory accesses. Okay, so that's why these are called quick adds sometimes. And that's basically all there is to an add immediate instruction. So I hope this was helpful. If you guys have any questions, I know I say this at the end of pretty much every module, but I definitely mean it. If there's anything I can do to help, please shoot me an email and we can meet up and talk some more about this. But I hope you found this office hour video useful, and I'll talk to you guys online soon. Thanks for coming.